Okay. Hi, everyone, and thanks for tuning to this week's Quantum Chaos seminar. A short announcement, Pablo couldn't be here this week, so it's just going to be me for today. So I'm going to introduce today's speaker. So it's my pleasure to introduce Daniel Ranard. He's currently finishing his PhD at Stanford University. Hi, everyone, and thanks for tuning to this week's Quantum Chaos seminar. A short announcement, Pablo couldn't be here. Okay, things have been solved. So today's speaker is Daniel Ranard, finishing his PhD at Stanford University. And before that, he worked at Harvard University and at the Perimeter Institute. Today, he's going to be talking about emergent classicality and about on the spread of quantum information. All yours, Daniel.
Thanks. So this is based on work with Xiaoliang Qi at Stanford, and it's also building off some work in 2015 by Brandau, Piani, and Hordetsky. So just the outline of the talk, I'll be talking about some constraints on the spread of quantum information. And I'll start by going through various examples and then work through what the general principle is that constrains this spread. And then I'll lead up to a actual precise statement of the theorem, because in the end, the main result here is just a mathematical theorem. And then I'll talk about the implications for many-body systems. Now, this theorem is going to apply to all dynamics, so chaotic dynamics, non-chaotic dynamics, etc. But some of the interesting examples will be from many-body systems where we have some chaotic dynamics. So I think that's what will be interesting to think about. So we're going to be asking how information can spread. We're going to be imagining some large lattice system. I think just say a 2D lattice of qubits like we're looking at here. And we have some small region A. And we're going to perturb A, maybe by inserting some extra qubits there or changing the state there. And then we're going to evolve. And after some amount of time, we're going to look elsewhere in the system and ask what we can learn about A. So that is to say, I'm going to look at some region like R1 or R2, and I'm going to ask, what can I learn there about the perturbation that happened at A? So let me just go through some examples, some heuristic examples of what sort of things could happen. So maybe we perturb A, then we wait a long time, and everything thermalizes. So now when I look at some small region R, what can I learn about A? Well, in this case, nothing, because the whole system thermalized or scrambled. Now, let me just say something about terminology. If I'm talking about information spreading, there's a few different things I could mean. In this case here, I'm going to say that the information didn't spread anywhere. Now, by unitarity, the information is still in the system somewhere. So if you look at the global state, you can still recover information about what you input at A. On the other hand, if you look locally, you can't learn anything about that input. So in that sense, I'm going to say that the information just went away, because in this talk, I'll be focused on what you can learn by looking locally in the system, not by looking at complicated global correlation functions. So in this first example of thermalization, the information didn't really spread, it just went away and is no longer locally accessible. Okay, here's another sort of example. Let's say this was a big chaotic tub of water, and then we made some splash in region A. So now, if we wait a very long time, the water settles down, and we're sort of like the first example. But if we wait some intermediate amount of time before the water has settled down, and we look at some region R1 or R2, then we'll see some evidence of what we did at the input A. So in that example, the information has spread throughout the system until everything thermalizes again. Now I'm going to be focused on lattice many-body systems. So if you want an example that's like that tub of water, but is not a tub of water, imagine, say, a Heisenberg system with a large on-site spin, so in the large S limit. And that model at intermediate times will look like a bunch of classical rotors spinning around and coupled to each other, and it has some chaotic dynamics. So that's just another example. If we whack one of these rotors and then we look elsewhere later, we'll see some evidence of what we did there. Okay, now here's another type of example. In this example, imagine that some quasi-particles at A are transferred directly to some region R1. So in this example, when we look at R1, we learn exactly what happened, what we did at A. But if we look at R2 or we look at R3, then we can't learn anything about the perturbation at A. Okay, here's another putative example. If we could imagine that the information at A got transported both to R1 and to R2. Of course, we know that that's not actually possible if by information we mean both the quantum and the classical information, and that's just because of no cloning. So you can't have the information about what you did at A get transported exactly to multiple regions. So we already see how the kinematics of quantum mechanics itself puts some constraints on how this information can spread and somehow differentiates between the quantum and the classical information. Okay, and here's my final example. Imagine that the system A is decohered by the remaining many-body system. So it's effectively measured by its environment, you could say. And then the result of that measurement could be passed to each of the regions R. So maybe A was some spin in superposition, and it gets decohered in the Z basis, and then information about that outcome shows up locally in R1, it shows up in R2, it shows up in R3. And in that case, the information can spread widely throughout the system. On the other hand, it's only the classical information, because whatever information about the phase of that superposition, the phase in the Z basis, that information is now gone. It is encoded somehow in the system globally, but when we look locally, we can no longer see that information. Okay, and the main result, in a sense, that I'll be talking about today is that basically all dynamics can be thought of as some combination of these latter two options. So some part of the system A might have gotten transported to some region. So some of the information in A remains quantum and remains localized in some region, perhaps. On the other hand, there can be other degrees of freedom in A that are effectively measured by the environment, and then that information can get passed around to different regions of the environment. So somehow everything is going to be within these latter two categories, some hybrid of that. And then I'll be describing a theorem that sort of characterizes how that works. So here's a picture sort of illustrating what I was talking about. So I'm going to have some region that I'm going to call Q that we'll also call the quantum Markov blanket. And when I give the actual theorem statement, that name will make a little more sense. But what it means physically is it's the region where there is allowed to be some quantum information that's locally accessible about A after this evolution. So that region Q, it might include A itself, it might be localized to some other region on this lattice, but that's where the quantum information about A is. And that region can't be too large. That'll be part of the main result, that this region Q where the quantum information can show up, it can't be that large. And then no matter where you look elsewhere in the system, as long as you're looking away from Q, so if you're looking at R1 or R2 or R3, then you can only obtain classical information about A. And moreover, the classical information you can obtain about A in one of these other regions R, it'll be classical information in the sense that you could have obtained it from some measurement in a fixed basis on A. And that basis of measurement will be the same for any of these regions R. And for now, those are just words, but I'll make that very precise as I go on. Like I said, this is based on a great paper by Brandow, Piani, and Horodetsky. They explored very similar ideas, and they also proved a theorem about this concept. The theorem that we're going to prove is a lot stronger, and the argument, I think, is a bit simpler and more constructive. And just to outline the difference between our results, what we call this region Q for them was allowed to be arbitrarily large, but nonetheless a small fraction of the total system size. Whereas we're going to be showing that this region Q is actually only order 1 size. So it really makes this more of a sort of monogamy of entanglement result, where we show that the size of this region Q where the quantum information can go just can't be too large, no matter how large the rest of the system is. Okay, so I've talked about a lattice system as if there's some sort of spatial geometry. But now, as I work towards making the theorem statement, we're actually going to put ourselves in a more general setting. So we're just going to imagine that there's some input system A, and then it couples to an environment that I'll call B. It doesn't necessarily have some sort of spatial arrangement. And we're just going to ask that this environment has many parts. So maybe it's made up of qubits, and it has n qubits B1 to Bn, and n is large. So we're going to imagine that we couple A to B, then we evolve everything, and then we're going to study the local subsystems of B. So we're going to ask, if Alice puts in her message at A, what can Bob learn about A when Bob is localized to one of these regions of the environment? So we're going to throw out all the other fragments and just focus on this one region. And again, the result will roughly be that for most BI, for most Bobs at their respective BI, Bob can only learn classical information about A. And to be slightly more precise, the statement is that almost everywhere in the environment, the locally accessible information about A looks classical in the sense that it can be obtained from a measurement of A in some fixed basis. Now, let's start setting this up more mathematically. We have some input state at A. We couple it to a state on the environment B that I'm calling tau B. So A starts out in a product state with B. Then there's some unitary evolution of the joint system. That can be some arbitrary unitary evolution. And then finally, we're going to trace out everything except one subsystem BI. And note that subsystem could be A itself. So we could consider A as one of the BIs. The point is just that we're going to restrict ourselves to some local region in the global system. So to make this more precise, we want to first understand what this squiggly arrow is as a mathematical object. And then I'll tell you why this map from row A to row BI is in some sense classical for most choices of BI. But first I need to define what that means for the information transfer from A to BI to be classical in some sense. So this will just take a brief foray into some basic concepts in quantum information theory. As you may know, a quantum channel from A to B, from some general A to some general B, is just some map on the space of density operators. So it sends some quantum state to another quantum state. It could be unitary quantum evolution, or it could involve some more complicated process. And so this squiggly arrow on the page before is just an example of a quantum channel from A to BI. And now I want to characterize a special type of quantum channel called a measure and prepare quantum channel. And these are the channels that are classical in some sense.
Hi, Dan, a quick question from the audience. Will it be necessary to start from a product state for this formalism?
Yes, it will be necessary that A starts out in a product state from the rest of the system.
Okay, thanks.
And so for instance, if your whole system is in maybe it's near the ground state, and therefore you might worry that this setup of having a product state between A and B will necessarily require us to introduce some energy, because the ground state will not naturally be a product state between A and B. So I think it is interesting to try to generalize to the case that there's some entanglement in the beginning, as is the case when you say have a ground state on the global system. So it's a good question.
Great, thanks.
So like I was saying, we want define this special type of channel called a measure and prepare channel. And these are channels that take this form here. And in particular, we're focused on the right-hand side. And the idea is that there's some measurement operators, M alpha on A, that form some POVM. And there's some states, sigma B on B, such that we can write the channel in this form. And when there are such choices that we can write it in such form, we call it a measure and prepare channel. Now, if you haven't thought about POVMs recently, you're welcome to think of these M alphas as just an orthogonal basis. Now, how can we interpret channels that have this form? Well, we can imagine this channel is being implemented in two parts, which you can see in the expression. First, we make a measurement of the system A that results in some outcome alpha. And then, based on that outcome alpha, we prepare a state sigma alpha on B. So this is a very special type of channel. For instance, the identity channel does not take this form. There's no way to write the identity channel as a measure and prepare channel. And one of the special features of a measure and prepare channel, or say the defining feature, is that if Alice and Bob at systems A and B are in different labs, then they can implement this channel using only classical communication from Alice to Bob. So the way they do it is Alice takes a measurement of her system using the POVM M alpha. So again, you can imagine she just projects in the alpha basis. Then she gets some outcome labeled by alpha, and then she passes that to Bob. That's a classical message. And then Bob takes that and he prepares some state on his system based on that outcome. Now, it could be the case that the sigma alphas are all the same. That's an allowed form of a measure and prepare channel. And in that case, it just means that even though Bob got this message, he didn't do anything with it, and he prepared the same state independent of the message. So for instance, the constant channel that replaces the input with a constant state is a sort of trivial example of a measure and prepare channel. Okay, great. So that's the only sort of terminology we'll need to import. And now I can make the statement. The statement is that for any evolution on the joint system that we chose, it'll be the case that for almost all BI, the reduced channel from A to BI, when we trace out everything else, will look like a measure and prepare channel. And moreover, the choice of measurement operators, this sort of basis of measurement that we use on A, it'll be independent of the BI. So there's some POVM such that for all the BI, or almost all of them, this reduced dynamics from A to BI looks measure and prepare using the same measurement operator. And in particular, for almost all BI except order 1 many, that order 1 region is what I called Q before, the evolution from A to BI looks like we did this measurement, we got the message, we passed it to that region BI, and then prepared some state. So I'll make a very precise statement of that in another few slides. But first, let me just work through some examples again, sort of like we did in the beginning, and see how this idea applies to them in different ways. So remember, there was this direct transport idea. That was one sort of setup where the information at A just gets copied over to B1, or transported rather, not copied. So the input system A sends something faithfully to B1. And now if we look at the reduced channels, the arithmetic here is pretty easy. The channel from A to B1 down here looks like the identity channel, whereas the channel from A to some other BI looks like the constant channel that, independent of the input, it just produces this state 0, 0 on the output. So does our statement hold? Our statement was that for most BI, this channel looks measure and prepare. Well, for B1, the channel is not measure and prepare, it's the identity channel. So the statement doesn't hold there, but of course the actual statement is only the claim that for most BI, it does look, measure, and prepare. So in fact, we do satisfy that claim here that for almost all the BI except one, it looks, measure, and prepare. Okay, another more interesting example is a spin chain evolution. So you can imagine that I have this spin chain. I have this spin chain B, and then I have another qubit A, and I tack it onto the end of the spin chain, and I evolve both of them, and then I look at one of these remaining qubits. For instance, it could be A itself. Now, of course, this example, I can't just work out for you unless it's some solvable model, but that's supposed to be the strength of the statement. So you can do this numerically, and you can check, you prepare B in the ground state if you like, you couple them, and no matter what evolution, what Hamiltonian you use, you'll find that the reduced dynamics to most of the BI, again, look, measure, and prepare. And I can show some numerics on that later. But first, here's an example that's slightly less trivial, but that we can work out. And this is just the example that the input qubit is effectively decohered. So imagine that the environment starts out in this 0 state, but then the dynamics, in the case that the input qubit is 0, it copies that 0 onto everywhere in the environment. Whereas in the case that the input qubit is 1, then it copies that information again as a 1 to everywhere in the environment. So in this case, this is the reduced channel down here. And you can see that it looks like a measure and prepare channel in a very straightforward sense. It looks like we measured the qubit A in the 0 or 1 basis. We passed that message to qubit BI, and then prepared the corresponding state 0 or 1 on this BI qubit. So this is a straightforward example where the system is decohered and the information gets passed around everywhere in the environment. And remember, I was saying the result is that in some sense, any channel looks like some mixture of this decoherence type channel and the direct transport type channel that I mentioned before. Okay, so now I'm about to make the actual theorem statement. And remember, we had this region Q that was called the quantum Markov blanket. And the idea is that Q will roughly include the outputs BI that have the most information about A. And Q is blanketing A in the sense that any information about A that is accessible on these small regions R can be obtained by just measuring Q alone. So Q somehow is like this buffer that contains all of the quantum information about A, all of the locally accessible quantum information. And again, the statement will be that you can take Q to be order 1. So let's see what the precise statement is here. I'm going to try to actually go through this so that it's not all just fluffy words. So we're going to start with some quantum channel, again from A to all of these, to this region B1, to this system B1 to Bn. And then for any output subset R, these are like my regions R1 and R2 from before, we're going to define this reduced channel, which again is just doing the dynamics and then tracing out everything but R. Okay, and now here's the statement. So I'm going to imagine that I let you choose the size of the region Q and the size of the regions R that we'll use. So you get to choose those sizes, and we'll want to take Q somewhat bigger than R for the theorem to be effective. And then once you choose that, I say, okay, there is a P of M, M alpha, some fixed P of M, such that when you look at the reduced dynamics onto every region R of size up to R that doesn't intersect Q, so you're looking at all of the subsets R disjoint from Q, then we have the following statement, that the reduced channel looks approximately like this measure and prepare channel that I'm calling epsilon. And note that this measure and prepare channel epsilon, or big epsilon, it uses the same POVM M alpha for every region R, although the states that it prepares on that region may well be different. So those may well depend on R. And now what do I mean by saying that we can take Q to be order 1? Well, as an example, let's say that N is very large. N is like 10,000 because we're working on a big spin chain. And let's say that we're going to choose R just to be 1 or 2 or 3. So the point is that we're going to focus on regions of that spin chain of only a few qubits and ask what information is locally accessible when we look at regions of this size. And now you can ask, how big do you need to take Q to be in this error bound such that this right-hand side here is small? We want to get small error for our statement. And the point is that the size that you need to take Q to get small error here doesn't depend on N. It only depends on R. So even though Q is 10,000, even though N is 10,000, we can take Q to be something like 10 or 100 maybe. And already we'll start getting a small error on the right-hand side, even if we had 1 billion qubits to start with. We can still take this same Q of 100 and we'll still get the same error. So again, the point is that no matter how big this overall system is, Q doesn't need to be that large and we'll already have a somewhat precise statement. Okay. Maybe I'll pause if there's any questions from any viewers at this point about the precise statement. I know we're on the questions are hard, but.
We can give people some time. There's a short delay between this presentation and the YouTube live stream. I think we're good. I think you can continue.
Yeah, sure. Okay, so I'm not going to give a full proof, but I'll sketch a few of the ideas, especially because the ultimate proof method is somewhat physical in a sense that there's a physical picture attached to it, and also because it yields a constructive algorithm for finding both this region Q, the quantum Markov blanket, and for finding the POVM M that I was discussing. So in some sense, we can find, if we have a system that is numerically tractable to begin with, such as a spin chain, then doing numerics on that system, we can constructively find that POVM M that is the effective measurement on a subsystem. Okay, so the first step in the proof is to realize that there's a very analogous statement for states instead of channels. And it's actually easier to prove this statement for states first, and then we go and prove the statement for channels afterwards. Now, the statement for states is interesting in itself, I think. So let me just say what that is. Instead of a channel, you consider some state on some large system. And I'm just going to take one of the subsystems and call it A. So there's no dynamics. We have a single state, and then one of the systems we're going to call A. And then we're going to look at the reduced state rho AR, where R is some collection of subsystems B1. I should have noted before, perhaps, that there's this distinction between the BI and the R. So the BI are just like the individual qubits of our system. And then the region R is some small region that may contain several of those qubits. So anyway, we're going to look at this reduced state on row AR. And the claim is that for almost any R that you choose, the state is actually going to look very close to separable. This expression on the right is just an expression for a separable state. So that's already an interesting property about the marginals of arbitrary quantum states, that for almost any BI you choose, its marginal or reduced state with A will look separable. And you can think of that as a sort of consequence of monogamy of entanglement. It can't be entangled with too many other qubits. But the special ingredient here that we add that makes this not simply a monogamy statement is that in this expression for the separable state, the row A here isn't going to depend on R. So that corresponds in the channel statement to the idea that the measurement isn't going to depend on the region R. Okay, so we have this theorem for states, and I haven't told you exactly how it's analogous, but the way that it's analogous, or really equivalent to the channel statement, is through this idea of channel state duality that's used often in quantum information. And it's a nice name for a pretty simple concept. The idea is that you take the tensor corresponding to the channel and you bend some legs around. Or more physically, you take the channel and then you take some, so here's our channel, and then we take some maximally entangled state and we act the channel on half of that maximally entangled state. So we have perhaps I shouldn't have called it R again, but we have a reference system that I'll call R briefly, and that's maximally entangled with A. And then we act the channel on A, and we get some state on the combination of the reference system and the output of the original channel. So that's how to go from a channel to a state, and vice versa, just by bending the legs around again. And this is a nice little duality because various properties of channels will correspond to various properties of states. For instance, the property that a channel is measure and prepare is equivalent to the choice state, that's the corresponding state, it's called the choice state, being separable. So similarly, the property that the reduced channel is measure and prepare, when you reduce onto some region, will be the property that the reduced density matrices on some region of the state are separable. So if you believe this, which is a simple consequence of definitions, then it's easy to see that those two statements about channels and states that I gave before are in fact equivalent theorems. So here I'm just saying that again. Okay, so now how can you prove this theorem for states? Well, I'll sketch the argument for a slightly easier version of the theorem for states. So it's sort of a warm-up of a warm-up, but hopefully it'll be illuminating. And I've put these definitions on the screen just in case you forget, for instance, what the conditional mutual information is. So here's the warm-up statement that is sort of a fun exercise to prove. It says that for any size, for any little q that you choose, you can find some region, big Q, such that the conditional mutual information of A with BI, conditioned on that region, big Q, is small if you take Q large enough. So if we take a large enough Q, then A will have small conditional mutual information with everything else. Okay, and how do we prove this? Well, we can use a sort of optimization argument. We can use a sort of greedy algorithm. So here's our greedy algorithm. We're going to build up Q, qubit by qubit, or BI by BI. So first, we're going to choose some region BI1, and we're going to choose it to maximize this mutual information. Once we've chosen that, we're going to choose another qubit that maximizes the additional information we get. So it maximizes the conditional mutual information conditioned on that first qubit. So we're sort of trying to greedily find qubits in the environment that give us the most information or that are most correlated with our original qubit. And we're going to greedily add those to our quantum Markov blanket. And we keep doing that until we stop at whatever desired size of the Markov blanket you had. And that size of the Markov blanket, again, will control the error in the approximation. So we stop wherever we want. And then we use the chain rule of mutual information. So we can add up all of these quantities that we had maximized. And we know that at most, they can only give this mutual information. Or sorry, they exactly give this mutual information using the chain rule. And this is just a telescoping sum here. And finally, we say, okay, well, this mutual information can't be that large because it can only be as big as the original system DA, the original size of the system A. And now by strong subadditivity, all of these terms are positive. So that's sort of where the meat of the argument comes in. And knowing that all of the terms are positive, and knowing that there's a lot of them if you choose Q large enough, and knowing that they have some constant sum, that means, okay, most of them, or at least one of them, say, needs to be small. They can't all be large if there's many of them and they have some constant sum. So that's what picks out this inequality here. And here's another sort of picture of what's going on in this argument. This is just a fun little picture. And we start with this region A. And now we're going to consider all the subsets of size 1 in the rest of the system. So maybe it's, and we're going to list those in this first column. The column is a list of subsets of size 1. And then the next column is a list of subsets of size 2. And the next column is a list of subsets of size 3, and so on. And we're going to choose some path of nested subsets. So we start with A, and then we add another qubit, we add another qubit. So these arrows are these nested subsets. And in a sense, we're optimizing over this space of paths. And as we increase the size of our region Q, then the information that we're getting about A will go up and up and up. But because it can't get too large, there'll be some sort of bottleneck point where it can't be increasing too much. So say here at this Q equals 2. And then that's the region that we pluck out to make this statement about low conditional mutual information at the top. So you can think of it as optimizing over the space of paths, greedily choosing out new subsystems until you've learned the most about A. Okay, so that's all that I'll say for now about the actual proof strategy. There's a couple subtleties I glossed over, of course, just because this is the warm-up of the warm-up. Okay, so now let me summarize a little bit and talk about implications for many-body systems. So like I said, to the extent that your system is numerically tractable, like a spin chain, then the output of the algorithm that the proof is based on, this greedy algorithm, is that you can actually construct the POVM on A. And so you get this special POVM on A that is sort of the basis in which the rest of the system is decohering that subsystem to the extent that it's decohering it at all. So again, it could be the case that everything thermalizes and then you learn nothing on each of these regions about A, in which case the POVM that you get from this algorithm won't be very meaningful, because the prepare part of the measure and prepare channel will be trivial. It'll prepare the same state independent of the measurement. So in that case, the measurement is not that meaningful because it doesn't really determine what goes on in each of these regions. However, in any less trivial case, in any case where you didn't just completely scramble, then this POVM M alpha will be telling you something about the way in which this subsystem is measured by the rest of the system. So the question is, how can we use this POVM to identify emergent classical variables in many-body systems?
There's a quick question before you continue. To clarify, you may have said it, but can you explain the physical meaning of the quantum Markov blanket? Is that a region that may possibly still encode the full information of the initial state?
Yep. Let me just put a, sorry, I just want to put a picture on the screen. So the quantum Markov blanket, it is the region where any locally accessible quantum information about A must be found. So if the system completely scrambles and there's no information about A that's found anywhere, then in fact you can take this Q to be empty. So in that sense, you don't even need a quantum Markov blanket and even with this empty region Q, any region R will look like a measure and prepare channel. On the other hand, if there is some quantum information about A that's present somewhere locally in the system, then Q will need to contain it. So when you, let's say you're doing numerics and you constructively find this region Q, it's the region where there is quantum information about A, if there is any at all.
Okay, you got an answer saying perfect, thanks, and that also answered the follow-up question on the connection with scrambling. So please continue.
Yeah. So when I talk about identifying emergent classical variables, let me give you a sort of simple example, which is, remember I mentioned the idea that this could be a Heisenberg model in the large spin limit, in which case each of these little lattice points is some large spin. And in that case, what you would find, I think, although I didn't run this particular example because I would need to run this in a large spin limit, so that wouldn't be numerically tractable to do it on a computer. Maybe you could do it analytically. I think what you would find is that the POVM that you obtain on A will look like the POVM that measures the direction of the spin. And although for spin half, you can't really measure the direction of a spin and get an answer without changing what that spin is, in a large spin system, you can have a POVM that does basically tell you, okay, where is the spin approximately pointing? So it would, I think, identify this classical spin, but again, I couldn't do that particular example. Here's another sort of example. We can do some simple models of hydrodynamics. So I'm sure many people are familiar with the idea of using random quantum circuits, local circuits on a spin chain. And in particular, you could do a random quantum circuit that conserves charge. So there's some U1 conserved charge that floats around and diffuses through the system, and everything else is sort of getting scrambled. And this is like a toy model of Hamiltonian evolution because there's some conserved quantity like energy, and then everything else is getting scrambled. So it's sort of like a toy model of a chaotic energy conserving system. Okay, so in this example, this is an example that I've actually done numerically. And you ask what information about A is sort of being measured by the rest of the system? And the answer is that the P of m you get roughly coincides with the charge on that system A, which is an observable. And this roughly makes sense because most of the information about A is disappearing when you do the circuit, in the sense that it's no longer locally accessible. But the charge information is having some impact on the rest of the system, even in a small way. So the charge information on A just diffuses, that charge literally diffuses. And if the system is finite, if the system isn't too large, then on every region R, you'll have some record of that original charge on A, although it's sort of averaged out by the entire system. So you have this sort of 1/volume record on each subregion after equilibration of what that original input on A was. So I've given you 2 examples, and then also the spin chain example that I'll show you numerics of in a minute here. Actually, let me show you that spin chain example before I finish up. So I mentioned before there was an example I had done numerically where you take a spin chain, you add an extra qubit, and then you evolve the joint system, and then you apply this theorem. So what I'm showing you here is the result of taking different Q on the x-axis, so that's different sizes of the region Q. And for different sizes of the region Q, you get some accuracy in the theorem. So the y-axis is sort of like the right-hand side of the bound. And physically, it's telling you how good of a Markov blanket Q is. So as you take Q larger and larger, you're going to get a better and better Markov blanket. And when the Markov blanket is better, it means that there's even less quantum information accessible on the rest of the system. So the reduced dynamics to the rest of the spin chain for a good Q look very close to measure and prepare. And so you're seeing that as Q increases, we're getting a better and better Markov blanket. And furthermore, we're seeing that at different times, so say at t equals 3, which is a later time here, you're going to need to take a larger Markov blanket in order to get a good blanket. You're going to need to take a larger region. And that's just because the information is spreading out on the spin chain. Now, it may look like at later and later times, you're going to need to take a larger and larger Markov blanket. It sort of looks like that's how these curves are trending, that at later times you need to take a larger blanket. Of course, the power of the theorem is that you actually only ever need to take an order 1 size blanket, no matter how long you wait. So even if the spin chain does all sorts of crazy things, you don't need to take a very large Markov blanket before saying, okay, almost everywhere else besides this blanket looks like only classical information has arrived there. Okay, so I was saying that it would be nice to have some more examples and think about how we can apply this theorem to different many-body examples, even doing it numerically, and ask what can we learn about the dynamics by looking at that effective measurement. I've shown you examples where we basically already know what the answer is going to be, but it would be great to look at some examples where you don't know what the answer is going to be, and it's interesting to find out. So that's part of what I see as future work. Another simple thing is, can this bound be improved? Is it actually tight? I think it's not completely tight, but the more interesting question is to ask, how can we make it tighter when we add more assumptions? Like if we actually have spatially local dynamics, which I didn't assume, or we have local conserved quantities, which I didn't assume, is the bound any tighter? And finally, I think one of the most interesting applications would be to use this algorithm that we have to identify these emergent classical variables in many-body systems. And I also have some hope that by doing that, you can make more efficient simulations of many-body systems. Okay, thanks.
Okay, thanks a lot, Daniel, for this really clear talk. I really enjoyed it. So as usual, we still encourage people to ask questions, though we've already had quite a few during the talk. So maybe ridiculous initial question, but where does the term blanket come from for the quantum Markov blanket?
Yeah, so the term Markov blanket is used already in the literature on probabilistic graphical models or on Bayesian networks. So it's this term from information theory or from computer science. And what it's meant to evoke by this word blanket is that it's the region that sort of covers the input region, in the sense that if you know everything about the blanket, then you already know all there is to know about the region A. So we're looking at some other region R, and if we do a measurement on A that sort of covers the input region, yeah. It's hard for me to justify the word covering but you might sort of have this blanket visual that this region is acting as a sort of buffer that covers the input region, and all the information needs to sort of flow through that blanket. So maybe that's one answer. Okay, it's also called a shield, by the way, sometimes, a Markov shield. Maybe you prefer that image.
I don't have any preference either way. And have you thought about applying this to many body localized systems?
Yeah, I think that's an interesting question. I haven't thought directly about what would happen. Yeah, I guess you have this logarithmic light cone as the information spreads, but I haven't thought about, what if you look at some late time when this logarithmic light cone starts to be larger, I haven't thought about what information is still locally accessible. So to what extent does the information spread out in a way that it becomes delocalized, or to what extent does it actually still remain locally accessible in some regions? That's an interesting question.
Okay, thanks. I think the audience doesn't have any more questions. They already asked all of them during your talk. So thanks again to Daniel for this great talk. Thanks again to everyone for watching. So next week, we'll be back with a seminar by Shreya Varden from MIT, and she will be talking about a universal approximation for entanglement entropies in equilibrated pure states. And if you want to keep getting updates about these seminars, you can either subscribe to this YouTube channel or subscribe to our mailing list in the description of this YouTube channel. So thanks for watching, and see you next week.